Thanks, Paul. I just want to check if you guys can hear me all right.
Yep, loud and clear, Artie. Can you hear me okay?
Perfect. Okay, so we might be able to start the webinar now. All attendees, welcome to Mimomax webinar. So me, myself here, Adi from Mimomax Wireless. Joining with me, we have Paul Reed, our CEO, and James Dow, our CTO, who's been working on this topic that we will discuss about quite a lot extensively with quite a lot of our clients. So for those of you who have any questions along the way, please feel free to drop in the questions on the questions panel you can find on the right of your screens. You can put on a chat as well, questions on that chat panels on the right of your screen as well. We do have a handout that we would like to share to you at the end of the webinar, or you can download it now as well, the right side of your screen. So we will now begin the webinar. So thanks everyone for attending. Paul, if you can move to the next slide of the screen that you're sharing, please. Yep. Okay, so Mimomax Wireless, we are founded in Christchurch in 2007. So now we have a couple of regional offices, mainly in Phoenix, Arizona. Our key target market is utilities, public safety, government, mining, transport, oil and gas. Now to save bandwidth, I was just gonna turn off my webcam for a second. And our solutions is a ultra reliable, high data capacities, fast and secure connectivity between machines and between people via narrowband radio communications. If you move on to the next slide, please, Paul, for our use cases. So here are the use cases that we have in point-to-point and point-to-multipoint communications. Now, we support everything from LMR backhaul, lease line, teleprotections, redundant backhaul, and point-to-multipoint, fans, SCADAs, and AMI connectivities as well. This particular webinar, we will discuss specific applications in teleprotections and how we use it to support GNT as well as IOU to maximize the functions of their fan network. So I'll hand it over to Paul from now on to present. Paul, if you can lead it from here, that would be wonderful.
Thanks, Artie. You can hear me okay?
Yep.
Yep, great. So thanks, everyone. So today we're going to be talking about teleprotection as it relates to communications, and this simple diagram here just depicts a simple scenario where we're protecting some high value assets. We've got 2 substations and switches, and essentially what we're doing is connecting wirelessly those switches, and what they constitute is a tripping scheme or a teleprotection scheme that will be operational in terms of trying to protect those high value assets. So some of those schemes that you come across will be familiar. They'll be mainly differential type schemes or transfer trip type schemes, and some of those are listed in the bottom left hand corner. And depending on what you're trying to protect and the speed and efficiency of doing that will depend on the type of protection scheme that you're using. What you'll see is our radios situated connected to those switches, and typically it is some form of synchronous interface that we'll be connecting to. So it'll be a high-speed fiber or G703 synchronous serial or X21, and the goal is in a fault condition, if something happens, that we're switching extremely quickly and protecting those high-value assets. So teleprotection in terms of mission criticality really sits at the top of the list with respect to critical communications, and has the most stringent requirements associated with that. I'll just continue on. So there are a number of options to consider in terms of teleprotection, and what we typically see where available is fiber. So you've got a very high data throughput, very low latency, low power loss. The challenge with that is sometimes you just can't get fiber everywhere. It could be a high install cost, could be subjected to damage, there could be lengthy deployment times, and it kind of excludes fiber from being an option. Microwave is the other commonly used technology when considering teleprotection. It's got a higher data throughput, so it's got a lower latency, but typically you don't need all of that bandwidth for teleprotection. The deployment can be lengthy. You've got some significant tower loading and engineering to consider, depending on the size of the dishes that you're going to be installing. Do you have the the real estate on the tower to be able to support those dishes? And then you've got a clear line of sight requirement, and sometimes not so resilient to weather, depending on where you're operating. And that's some of the challenges. So the big one really is where Mimomax come in, is where our customers are looking for a rapid deployment. It's an economical solution. There's a long-range connectivity requirement and high reliability. The resilience to weather is required, and obviously where you're seeking low latency. The downside with the Mimomax Narrowband is that you're not going to get a high data throughput compared to microwave or fiber, but quite often for teleprotection, data throughput isn't the highest requirement, and it is more about reliability and resilience. I think one of the reasons why we can achieve that is because we're operating in the sub 1 gigahertz bands. So in the United States, that's 900 megs, 450, 700, and around the world, we're doing deployments typically in the 450, 470 meg bands. So why else would you consider perhaps Mimomax narrowband technology when considering teleprotection? So we are proven extremely resilient in weather events, so you don't suffer the same weather fading phenomenon in 400 or 900 megs as you might do in 6 gig or 11 gig microwave technologies. So from an emergency point of view, and when things go wrong from a weather point of view, it's a very, very resilient solution. So the imagery on the right there points to earthquake zones and flood zones, two scenarios that we've been very familiar with in New Zealand of recent times. And in both occasions where the Mimomax links have been working, they have continued to work in those events, whereas other things wouldn't. So the light pole or the street pole on the right-hand top corner there, even though that's tilted almost 45 degrees, antenna towers were also tilted in these zones. However, because of the forgiving beam width of the low frequency antennas, we were still able to maintain communications. Likewise with Cyclone Gabrielle that came through, on the bottom right-hand corner, a massive flooding event, a lot of rain, but the links were stable for our mission-critical customers in New Zealand. So the other thing is that we don't need to rely on a direct line of sight. If we've got some clutter in the way, or potentially some other obstruction, because we're operating in those sub 1 gigahertz bands, we don't need to be pinpoint accuracy. And that's probably talks to the fact that we're still operating when your antenna has been tilted almost 45 degrees. The other thing is that we can support various modulations, so we can dial down to QPSK if we want additional fade margin, while still providing the bandwidth typically required for teleprotection. So that is a few reasons there why to consider MIMO in the narrowband space. In addition, we've got connectivity for new generation. So the cost is the other big one that I should touch on. Really, it's the lower cost of install. So we've got a small form factor panel. We've got a very, very integrated radio solution with duplexes and everything built in. And it is not a lot of tower real estate, and it can be mounted sort of on a pole mount. Example there of a customer who's just simply mounted their antenna on the side of a building to achieve a link. And that was something that was put in to help a customer that was having a problem with another link. So it started off sort of being a temporary structure, and then later on they continued to utilize that technology, and it became the primary linking system. So less tower loading, utilizing narrowband antennas, shorter deployment timeframes compared with fiber or microwave, probably less engineering required as well, and a very cost-effective option for connectivity, especially in remote environments. So some of the key technical considerations when we're considering teleprotection really comes from three main requirements, and probably four if we consider jitter, but latency, the requirement for category 1 latency is sub 6 milliseconds, and you know, certainly less than a cycle time, and asymmetry is the other, and we'll talk a little bit about that. I think the standard typically says 2 milliseconds, but you know, we're sort of seeing requirements less than 1 millisecond or 0.8. I think the MIMO technology sits around 0.4, depending on where or what equipment what interfaces you're using. From the standard, the availability is 3.5 nines, so 99.95% of availability. However, in reality, we'd be shooting for something more like 5 nines. If we could get that happening, that would be what we'd be probably setting out to engineer up front. So the dependability, you know, is based on the path planning, getting that right to support stable latency and jitter. Often our customers won't simply deploy only teleprotection. There might be an RTU, low bandwidth SCADA connected to it, or some other DA device connected. In the earlier days, we were also providing VoIP lines to remote workers as well. So you would have a VoIP circuit, you would have also an RTU connected, and you would also use that link for your teleprotection requirement as well. The way we do that, we put the highest priority on teleprotection when we're linking that, and there's dedicated packet sizes that are allocated to that. So it can be a redundant link as well. So if you have got a link that is very, very critical and you have no redundancy around that link existing, whether that be fiber or microwave, then some of our customers will choose to consider Mimomax as a redundant option, which could potentially be a lower cost option for them. And then the other typical requirement which comes in, which is really obvious probably, is security around this type of technology. It's not the sort of, teleprotection is not really the sort of thing you can do on a public network in any case. So moving on. So when we look at the categories of requirements, these kind of categories can be found in some of the ETSI standards in particular in Europe. So ENA TS 4867 is one of them, and it depicts the types of latency that are required for various categories of teleprotection. So 6 milliseconds being the most stringent and 30 milliseconds being the most relaxed. In any case, you know, this imposes the most stringent requirement on QoS to maintain fast, secure, and reliable comms. Typical latency rates that we're seeing are between 5 and 10 milliseconds. However, a lot of our customers are shooting for category 1 requirements and using Mimomax equipment to achieve that. This table here, it's a bit of a loud image, but it's designed to depict the latency rates across the radio, and what we're looking at here is the one-way latency, and what we're showing across the top is the relationship to latency versus bandwidth, and then the relationship to latency down the left-hand column is with a couple of interfaces that we use. So D37 will be the fiber, and G703 will be the audio-based sampling. So what we see here is with the 75 kilohertz, if we were achieving even QPSK, we would be 3 milliseconds. At QAM64, that improves, so we can achieve 1.9 milliseconds with the fiber interface. In the 50 kilohertz channel, we obviously get a reduction. As you lower the bandwidth, things take longer. So typically in a 50 kilohertz channel, hitting QAM64 will be at 3.1 milliseconds and QPSK at 5. So even at QPSK in a 50 kilohertz channel, we're meeting the category 1 requirements. And then as we go down to maybe what is more typical in some deployments, although most of our customers can still license 25 kilohertz channel, then if we're hitting QAM64 on a fiber circuit, then that's 4.8 milliseconds, still meeting those category 1 requirements. The area where we don't meet category 1 and we sort of have to move towards category 2 is area where we're in the 12.5 kilohertz space. For instance, if we were hitting QAM64 on those links, then that would be resulting in a 9 millisecond one-way latency. So the Mimomax radio, if you're not familiar with it, it is a combination of everything that makes radios quick. So it is MIMO. So immediately when you consider MIMO, you get a doubling of throughput. And that throughput is significant. So if you consider how much QAM you would need to create a doubling of throughput, then in terms of the MIMO case, if you said, well, we were hitting QAM 256 now, that MIMO benefit is equivalent to hitting QAM 65,000, which we know is impossible. So that is a significant boost to the capacity, throughput, and latency of the technology, which is why we're able to achieve what we have been able to achieve. The other component of what we've built into the product is a full duplex component. So it's got 2 transmitters and 2 receivers in that tiny box, along with both of the duplexes as well. So everything you need is contained in one unit to achieve this goal. And that can be mounted simply in a 19-inch rack or wall mounted or DIN mounted or even pole mounted outdoor if you should choose. We've also incorporated high order modulation. So we were one of the very early to go with QAM 256 and QAM64, 16 QAM and QPSK are the other options. And then the other big thing that we've got in here is QoS traffic management systems that allows us to manage the teleprotection latency requirements and priority really carefully. And the model of radio that we typically direct towards teleprotection applications has been optimized for teleprotection and how we set up the packets and how we prioritize traffic as well. So that helps us to keep that latency and overhead down. But MIMO, full duplex, high order modulations, and very smart traffic management within this product is really how we achieve our goal. So asymmetry, when we come to talk about that, it really is relating to the time it takes for an uplink and a downlink and the delta between those times. So what we're trying to do is get the difference in the uplink and downlink delay as close as possible. And it has to be very accurate for the teleprotection schemes that we're dealing with, because that is sometimes that delay will be the thing that determines whether a fault is valid or not. So you don't want a false trip, so you want to try and get that asymmetry delay as low as possible. Otherwise you fall into the category of potentially false tripping. To depict that, it's really going back to the diagram that we presented earlier and looking at, that's the link that we're looking at, is what is the difference in time delay between the blue path and the red path, one being the uplink, one being the downlink. So really trying to minimize that. So that is the goal with asymmetry, is to sort of bring that to a very low delta. These are some of the typical numbers that we would see. And again, in this case, it's not really dependent on bandwidth. So whether you've got a 12.5, 25 or 50 kilohertz bandwidth, we're typically seeing the same difference in delay between the up and downlink, which results in an asymmetry around about 0.3 of a millisecond if you are using RS422 synchronous serial, or if you're using 3794 fiber, you'd be seeing about the same. Picks up a bit for G703, and X21 is the most synchronized solution that we're showing here. So they are the typically the asymmetry numbers that we're seeing across the link. When we're looking at jitter, so jitter, like asymmetry, is again related to measuring delay, but this time we're measuring the delay between different packets arriving. So if we look at a bit of a journey for bit number 1, so that arrives and traverses the link, it takes 2.2 milliseconds to get across that link, and then another message arrives, and then it takes 2.199 milliseconds, and it's really the difference between those two transmissions that determines the jitter. So really the jitter is the delay that varies over time, and in this case we're showing about a one microsecond variation. But really it is important to minimize both of these for this critical application. So minimizing asymmetry, minimizing jitter is really key to ensuring that we're not getting false trips and we can operate efficiently and reliably in this environment. So some key engineering considerations to consider. So when we're kind of considering teleprotection linking with narrowband, what we would typically do for our customers is offer a desktop study. So it would be if we're going to do a basic sort of simplified study just to ensure that the link would be viable, then we might use a tool for radio mobile or using radio mobile and have a look at that and just say, yeah, this is a viable link. And Mimomax do that for our customers all the time. We don't charge anything to ensure that the link initially looks viable. If we want to move into a more formalized tool and properly engineer and report on that link, then we would bring out a client services team in to do a proper path loss study with a goal of making sure that we're designing to 5 nines. And other times we would be supporting our customers with helping them to model the links, providing the antenna profiles and the radio profiles as well. Licensing, so if there is not obvious spectrum available, then we help our customers find that license, and we've got a licensing service in the United States that we can work with our customers on finding spectrum available. That could be in the 900 meg band, it could be in the 400 meg band, it could be in the 700 meg band. Line of sight survey, RF survey, so often our customers have a very good view of their sites and understanding of those sites. They know what is on the tower, they know what will be co-located, but sometimes they will want to have support, and Mimomax can do that as well in terms of assisting with site surveys, noise analysis, and RF surveys, but typically making sure that the noise floor is not going to impact or has been taken into consideration when we've come to the final design. And the last thing is the noise survey. Somewhere within there and potentially between vetting that the link is viable and the licensing is making sure you're comfortable with the MIMO equipment and that you've had a chance to demonstrate that or exercise or evaluate that on the bench with the teleprotection equipment that you will be utilizing. So often important to make sure that before we go into the field or do anything, and this is typical practice in any case, that we've had a good solid bench test and made sure that everything's working as it should be. One of the big things when considering the type of environments this equipment is going in is electrical noise. And given we're in noisy substations and environments that sometimes aren't conducive to sort of the ideal scenario, being mindful of the spark transmitter or switching transients that happen in these substations, And this would be a good example of where we'd want to carry out a noise floor test and look at the peaks of those transients. So if those transients are hitting peaks and that are significant, then they eat into your fade margin and your noise margins. And that eats into your availability. So getting a sense of the environment, the radios that we have built-in noise floor monitoring functions, so we can run those radios for a period of time, log that data, and get an understanding of what is the environment that we're operating in. And it also helps us to, make sure we're designing the correct signal to noise ratio, allowing us to hit the BER requirements that are required. And in this instance, a little bit of site engineering may be required to figure that out. So obviously with switching transients, because it's often a very fast transient, if you consider the Fourier transform of that, and you've got a very broadband noise source, and if you start to point your antenna into that switch yard, then it will generally receive all of that energy, being these broader beam antennas. So that is just something for consideration when looking at electrical noise in these environments. Clutter is the other one. So typically with the types of technologies and the bands that we're working in, typically static clutter is less of a problem than moving clutter. So we want to try and stay clear if we can of particularly fast moving vehicles, trains, etc. Sometimes we can work through that, but in the ideal scenario, you wouldn't have a lot of movement in the link. So ideally, what we would be doing is not shooting into trees or foliage or buildings or anything like that, and the antennas would be all sort of a clear of immediate clutter. So when we say immediate clutter, the most important region to consider is around the launch of the antenna. As that clutter gets further away, it has less impactful, but less impact. However, if you're launching into trees or things, then that is much more impactful than having those sort of halfway through the link. Allow for some site engineering, initial and annual removal of foliage. So there might be some sites that we would look at and say, well, actually you've got a big tree growing there that could be impactful. We may want to do some work on that foliage just to help with this link a little bit. And that can be considered at site engineering time. And then just being mindful of, are we adjacent to a road, some form of busy highway or a railway? Obviously, are we in a flight path or shooting across an airport somewhere, or is there anything fast moving in this path that could be impactful? So when we're starting to talk about teleprotection and high availability, we really want to make sure that we've given consideration to the environment. So the antenna emplacement is quite important as well. So what we're having and seeing here with MIMO technology, and whether it's Mimomax technology or other MIMO solutions, both of our polarizations are incorporated into one antenna. So you've got the horizontal and vertical incorporated into one antenna. That's generally a small form factor panel that we're utilizing. If you consider the size of a pizza box in 400 megs, and if you consider perhaps two pizza boxes in 900 megs, that's the size of the antenna that we're considering. Important to understand that really we don't want to be shooting into a switch yard or into foliage as discussed. So having a decent height is important. 20 to 40 feet is typical, and they would typically be what we'd be modeling at. Some of our customers in the US have the luxury of some very tall towers, so it might not be unusual to see 100 or 200 feet of height for some of those towers. So just mentioned the switch yard, so just to minimize any impact of electrical noise, but also to kind of lift us out of the immediate clutter. and need to manage the compromise between increasing height and ability to reuse frequencies for another link. So frequency reuse is important. It is sometimes some work has to be done to achieve the channelization, and when that is coordinated, the higher you are, then the reuse factor becomes less. So consideration to the network in terms of how do you efficiently reuse, and that's often a trade-off between power and height and the frequencies that you have available. Optimizing spectrum. So some of our customers have the luxury, particularly in the US, they've gone and purchased the 700 megahertz upper A block, for an example, and this gives them 1 megahertz chunks of spectrum in the 757 to 758 and 787 to 788 meg bands. And this example really just shows that how they're utilizing that spectrum, and they will partition off a number of channels for teleprotection. The rest of the network may be a point to multi-point network supporting SCADA or AMI backhaul or substation automation, and quite often we find I've still got some spare channels to work with. But because we want to make sure that the priority of teleprotection is ahead of others and the QoS is configured as such, we would often encourage our customers to dedicate channels to that. So the 700 meg is one option. The other one is 900 meg space data option. The other is FCC licensed channels in the US, so 900 or 450 meg bands. And the other option is in the rest of the world is typically 450 to 470 is where we find this technology being most utilized. In terms of the radios themselves, so we have the Tornado radio, as I mentioned earlier, is self-contained. Duplexes are all built in. We have Ethernet and serial interfaces natively on the product. It's got a very, very low latency for point-to-point. It's, as we discussed, as low as 2 milliseconds, depending on interfacing and channelization. It supports the MIMO. QAM256 is our highest throughput, but that also equates to the lowest fade margin. So typically what we would, if we could hit a 256 channel, that would be great, but typically we see these applications in around 16 QAM or 64 QAM. And even with that, there's still enough bandwidth to run alongside the SCADA requirements. We do have the sophisticated quality of service built in to ensure serial teleprotection priority on the products. And the wide power supply range of these radios means that you can operate from 12.5 up to 60 volts, and the power supply is isolated so that you can use negative rails or positive rails. It doesn't really matter. We do have a PoE capability, so for some of our customers, they might like to just simply mount the whole radio up the tower or up the pole and bring that close to the antenna and just simply run PoE Cat 5 or 6E up that cable, up that tower to support the power requirement. We mentioned the full duplex component, and that is a requirement for teleprotection just due to the symmetry. You can't get away with a half duplex requirement or simplex requirement in teleprotection, simply because the asymmetry needs to be well aligned. We do have the inbuilt filtering, so the duplexes that are built into the product are bandpass filters. They're relatively narrow. For 3 or 4 megs, I think, is the 3 dB bandwidth on that filter. So the skirts rapidly push out to give a 60 dB isolation. So if you are in a noisy environment, you've got a number of competing technologies on a tower, you could be concerned with blocking and the likes. The duplexes in these radios are very good in terms of knocking out potential blockers due to busy and noisy sites. Redundancy. So while many of our customers will utilize Mimomax as a primary solution, we can also be utilized as a redundant solution, or we can be utilized as a primary solution with redundancy built in. So we do have redundant 1+1 point-to-point linking products in the Tornado family available. They are hot swappable for minimizing the loss of data. They also have a redundant antenna system if required, and can also be deployed as a redundant link as a primary solution, as I mentioned. Routing adaptation protocols are also built into the product. So if you want to adapt routing, that allows us, well, actually that's what we use as the mechanism for linking to the failover radio. So we use the MRAP solution in the product to allow us to rapidly fail over to the other redundant radio. Some of the testing that's been done. So we have been working with many customers over the years that have deployed teleprotection solutions. Puget Sound Energy out of Washington State is one of them. They've looked at this with respect to some of their switcher line protection relays and looked at characterizing the impact that the Tornado radio has had on the latency. In this case, they started with a benchmark of a back-to-back relay and measured 17 or 18 millisecond delay, and then they inserted the Mimomax Tornado radios into that link and looked at what the delta in terms of the return time latency was. And what we're seeing there is for the SAM 16, 25 millisecond latency resulted in 4 milliseconds of delay, and 64 QAM it was 2 milliseconds, and QAM 256 they got down to 1 millisecond. So this was an example where the customer had available the 757 or 787 meg band, and they decided to do this test to just confirm that the latency was as it should be, and I think it actually performed a little bit better than what we'd published. So it's a good example. The teleprotection case study that we've done here in the UK, this was based on looking at various teleprotection applications, but the goal here was to really have a cost-effective radio system and have that approved for electricity network providers in the UK for teleprotection. So what the goal was behind this was to provide a cost-effective solution that was obviously cheaper than fiber or microwave, and it was more practical in terms of deployment. Typically in the UK, we don't have the luxury of high towers, although they are there. It is a frequency reuse issue because spectrum can be challenging in the UK. They don't have the luxury of buying 700 megs or 900 megs. They are really constrained to the 450s and around those bands. So finding a solution that could be deployed in UHF or VHF was really important. So in these environments, because we are looking at environments where there is quite undulating terrain, there's often no clear line of sight. There's a lot of buildings and trees close by just due to the density of the population, etc. in some areas, then it is a challenging environment for teleprotection applications. So in this study, the results were tested against the Category 1 requirements. So that was the the requirements to be less than 6 milliseconds latency, have the high availability, at least beyond 3.5 nines, and also looking at symmetry meeting the 0.4 milliseconds and jitter requiring at least plus or minus 100 nanoseconds. So those results were tested in the field, and one of the links there that we're showing on the bottom right hand corner is one of those links that exhibited a little bit of clutter in the path and achieved that requirement. So that was a really good study to be undertaken, and a good example of teleprotection and how it would operate in the market. In fact, it was discovered because the particular customer that did this testing tested a number of different products and came to the realization that it was really only the MIMO full duplex radios that could achieve the requirements of teleprotection. So at least in the sub 1 gigahertz band, doesn't include any microwave that can test it, so or achieve it. So that was a good example of a case study in the UK as well. So I think that sort of brings us to the end of my technical presentation. We are going to be at UTC Telecom and Technology 2023. That will be in Fort Lauderdale in Florida. So if you're around that area, we'd love to catch up and talk a little bit more about this technology. We have got a Q&A session opening up, so I'll hand it back to Artie to facilitate that question and answer session. And thank you everybody for listening in.
Thanks, Paul, for the presentations. That was great. For those of you who have questions, feel free to just drop your questions down in the questions panels on your right corner. You should be able to see it over there. I know that we've got some questions coming out along the way while you're presenting, which is great. I would like to invite Paul and James to turn on their webcam for this sessions. Be able to so then the attendees will be able to see you. Great, thanks. I think one of the questions that pop up while you're presenting, Paul, and this is probably what James able to elaborate a little bit further in terms of teleprotection solutions, was the full duplex requirement, and why do we need that for teleprotections? James, if you could elaborate that a little bit further.
Yeah. So in a narrowband channel, to use a half duplex solution, the transmitter and receiver have to keep being switched on and off. And it takes a chunk of time to switch over between the transmitter and the receiver. And that means to keep a synchronous flow of data through the data interface, C3794 or X21 or G703. There needs to be a lot of buffering at each end. You need to, while a radio's receiving, it's got to buffer up the data that's then going to transmit in the next time slot. And the radio on the other end's got to then play that. And the stringent latency requirements can't be met when you're trying to switch directions all of the time.
Sorry, Artie, are you on mute?
Sorry, I just accidentally click on mute, but yeah, thanks for that, James. I believe with that we can say that half duplex radios would probably not be able to perform in a narrowband space for teleprotections. The other questions that came through is the interfaces for teleprotections. What sort of interface that you support with Tornado radios? James, is there something that you be able to answer to?
Yeah. Yeah. So the Tornado radio that you saw in the images, and that it's got natively, it's got Ethernet and RS-232. We have some small form factor converters that allow us to then provide other interfaces. So we have C3794 fiber, both with the standard multi-mode that is spec'd in the C3794 standard, and with the single mode variant that many teleprotection relays also support for longer fiber runs. The G703 interface, we support the 64 kilobit per second codirectional mode, and that's quite commonly supported by teleprotection relays, and X21 and RS530. So there's 3 different variants of the interface converters that allow us to support those. The G703, X21 and RS530 are all electrically isolated on the interface, so we can prevent ground loops between the grounding of the protection relays and the grounding of the radio and antennas. The C3794 being a fiber interface is electrically isolated anyway. I think that covers that, does it, Artie?
Yep. Thanks for that, James. The other questions that just popped up is probably for Paul. In the UK example, which band did they choose for the non-line of sight part? Was that the UHF or VHF band?
Yeah, I think the both. Well, the link that we were showing there on the presentation was actually a VHF link. So the link that we were initially focusing on was VHF, and that worked fine in that scenario, and it met all the requirements of the teleprotection category requirements for the customer. So that worked quite well. However, what they did discover was that in the VHF band, you do have a higher propensity for electrical noise, and just needs a little bit more engineering to manage that. So I think the school of thought was that UHF would be a better option if licenses were available. However, it doesn't discount VHF. The only real issue was around making sure you've engineered that site such that because of the more dominant noise components in that band, you've taken that into consideration. So yeah, that's what the outcome of that was.
Thanks for that, Paul. The other questions that came up is it for probably for James in the compliance piece for 900 megs. What sort of compliance do we have for FCC and IC Canada as well in 900 megs?
Yeah, so 900 meg radios, we've got compliant to FCC Part 101 from 12.5 kilohertz through to 75 kilohertz bandwidth. And we've got FCC Part 24 compliance for 12.5 through to 50 kilohertz bandwidths. The FCC Part 24 compliance is applicable to the Spectrum Space Data cell. In Canada, we've got Industry Canada RSS 119 compliance between 12.5 and 75 kilohertz.
All right. Thanks for that, James. And there's another questions about encryptions as well. And what sort of things do we use in terms of encryptions, and is there any impact on latency for teleprotections? That.
Yeah, so on our Tornado, we offer AES-256 encryption, though in the current implementation that's applied to the IP data, and the teleprotection data is set outside that, keeping the latency as low as possible. Would be possible via a firmware upgrade to add encryption to the teleprotection interface, but there would be a latency increase.
All right, thanks for that. There's another question, there's a couple of questions actually around our engineering over the rugged terrains and clutter and obstructions, probably for Paul a little bit more. So how do we ensure that we've got 5 nines reliabilities? Do we, is it more accurate for us to suggest a height over the surrounding clutter or obstructions, or is there any other keys that we need to consider right there to ensure 5 nines reliability?
Yeah, so it does come into a number of factors. So the first one is making sure that we're not sort of, as I said, launching into a lot of clutter. So around the initial site surveys is making sure we haven't got a lot of foliage, or we're not pointing the antenna directly into a building or the likes. So, you know, the heights that we were looking at with respect to the UK link, for instance, they were quite low and typical of UK deployments. So they were probably only, you know, probably about 14 feet, 15 feet, might have been hitting 20 feet. So they were quite low. There was some obstruction that was in the distance, but yeah, we were able to manage that with the link. Typically, the other thing we want to make sure about is making sure if we've done a noise survey at the ends of the link. As I mentioned, the radios have built-in noise performance measurement capability. If we're running that for a while and we can see that, hey, look, you know, this is the noise floor in this environment, or the peak noise floor, then we simply look to design a signal-to-noise ratio that gives us the margin to hit the modulation we need. The other component there is making sure we've considered, you know, the overall fading margin as well. So, given that we're in an environment, an RF world, where signals can change in the environment and fading can be impactful, typically we'd be shooting for more than 20 dB of fade margin to try and hit 5 nines, but that also depends on what obstructions or clutter is in the link and how far that link is. So a number of things there which we all take into consideration when trying to get, you know, move towards a 5-9 linking scenario. The requirement that was tested in the UK, you know, they tested it against the 3.5-9 type of requirement, and you know, that was suitable for the teleprotection application that they were looking at. Thanks, Artie.
All right, thanks for that, Paul. And probably last questions that pop up as well in terms of protections or protections. Do we support the 4-wire audio protections as well, James? Is this something that that we support as well?
Yeah, we support 4-wire audio teleprotection. So we've integrated that and tested that with a couple of different protection relays using 4-tone audio protection. That's typically been for a legacy application. Not really seen that for any new teleprotection installs, but where there's a existing teleprotection scheme with 4-wire connection, and the circuit, 4-wire circuit might be provided through lease lines from the telco, and can replace that with a radio solution if the telco is no longer guaranteeing latency, or the costs of that lease line are increasing.
Okay, cool. Thanks for that, James. I think we reached the end of the presentations. I believe that's all the questions that you have. Thanks for those who are attending. As for what Paul mentioned previously, we will be at UTC next month. So if you want to learn more about what we discuss here, please feel free to stop by. Grab some New Zealand goodies as well that we'll bring up. And yeah, have a chat with one of our team. So Paul, if you move on to the next slide, please. So you will see all of the contact information for all of our sales team right here. Feel free to reach out to each of these persons who's belong in your associated regions for more information, or if you'd like to learn more about what we do and the tests that we've done as well, you can feel free to do that as well. Again, there's a hands out that we leave here that you can download on the right side of the panel under the handouts area. Feel free to take it and download it for yourself. If you have any questions, feel free to let me know or anybody over here. And yeah, I think thanks again for everyone who attending, and I'll see you some other time. Thank you all.
Thank you, everyone. Thank you.
Thank you.